Good morning, good afternoon, good evening, good wherever you are, and welcome to another SNIA live webcast, this time on understanding persistent memory. Welcome to this webcast. I just want to explain a few things about the interface before we go any further and before I explain who's going to be talking to you or who I am. First of all, you've got a presentation screen in front of you. You can expand that to the full size of your desktop, laptop, whatever you're using to view this. And secondly, you have the ability to ask questions of our presenters today. And lastly, as you leave, I'd ask you to rate this presentation and tell us how well we've done. You can score us from 1 to 5, where 1 is, goodness, I wish I'd stayed on the golf course, to 5, excellent, I want more of this kind of stuff. So as I say, thank you for coming along today. Without further ado, a little legal notice. This presentation is the property of SNIA, and should you need to use it, that's fine, we don't mind. Just make sure you retain the copyright statements that we have on the slides. And secondly, if anything you do with these slides causes whatever you're trying to do it with to break into 2 parts, both the parts are yours. This doesn't come with any warranty, and you're using it at your own risk. So today, I'm the moderator, Alex McDonald from NetApp. I'm the co-chair of the SNIA Solid State Storage Initiative. Try saying that with false teeth, quite difficult. And I'm also an advisor on the SNIA Technical Council. Today I'm joined by Rob Pegler, who's a director on the SNIA board and senior vice president CTO at Symbolic IO. Good morning, Rob.
Thank you, Alex. How are you?
I'm very well. We also have Stephen Bates, who's a member of the SNIA Solid State Storage Initiative and the NVM Programming twig. And we're going to be talking more about NVM Programming shortly. And he's a CTO at Ideticom. I think I've got that right. Good morning, Stephen.
Good morning, Alex. Thank you for having me. Very excited to be here.
That's good. And last but not least, we have Arthur Senio, who is co-chair of the SNIA NVDIMMs segment. We'll be talking again about NVDIMMs, which is the packaging for this persistent memory that we're going to be talking about today. And he's the director of product marketing at Smart Modular. Morning, Arthur.
Hello, Alex. Thanks for having me today.
You're welcome. So, what are we? Who are we? What do we do? The Solid State Storage Initiative, as part of SNIA, which is the Storage Networking Industry Association, is here to educate to both 2 kinds of communities, the developer community and users. And today we're going to be talking to you about persistent memory and solid state storage. We're also here to develop and promote models and architectures, of which we have a few that we want to discuss today. And we also collaborate with leading industry alliances and organizations to make sure that this wonderful industry that we're in, which is going through a period of huge change, which persistent memory is one of the most interesting that I can think of in the last possibly 2 or 3 decades since the introduction of spinning disks all these years ago. This is one of the biggest advances we've seen. And we're here to collaborate and make sure that this kind of technology gets out there into wider use and is basically better understood. So today's content, where we've done the introductions, we're going to do a persistent memory overview. What do we mean by persistent memory? And you'll note during this presentation we're talking about a very specific set of technologies, and our speakers today will take you through what is meant by persistent memory. Then we'll talk a little about the non-volatile memory programming model, that's NVM. It's actually persistent memory, it's perhaps a little badly named. If we could go back, I suspect we'd scratch the name non-volatile memory and call it the persistent memory programming model. And then lastly, we're going to talk about the actual physical implementation of these things. How do we actually package up persistent memory and put it inside servers and storage arrays and et cetera, et cetera. So without further ado, what I'm going to do is I'm going to ask Rob Pegler to start us off and talk about persistent memory. And remember, during Rob's presentation, if there are any questions you want to ask, please do so, and I'll ask them on your behalf as Rob goes through his presentation, as Stephen goes through his, and as Arthur goes through his. Rob, over to you.
Thank you, Alex, and good morning, afternoon, evening, everyone. Very happy to be with you and give you a fairly brief 5 or 6 minutes, perhaps, overview on the topic of persistent memory. And as Alex said, perhaps further acquaint you with some of the terms that we use in the industry. That will help you to understand the deeper dive material, which is to follow from Stephen and Arthur. Very good. So let's talk a bit about the convergence of memory and storage. And this chart is relatively busy, but I think you'll get it. Starting on the left and in time, we're looking at today's technologies and, more importantly, the architectures for both, as Alex mentioned, servers and storage arrays, about how they use what we've known for decades now as memory and storage. And in particular, when we say memory, we mean byte addressable technology, typically used by processors, and then storage is typically block addressable and has come in many forms over the decades, in particular rotating disk and solid state disk now for the better part of a decade. And then you see at the leftmost pyramid, we of course have been using DRAM or dynamic RAM, typically in DIMM form, so very familiar manifestation of volatile memory. And the word volatile, of course, very important. In other words, it does not persist its data upon power loss, whereas the storage technologies that we know and love are made of persistent media and therefore retain data across power loss. Now, as we move to the right and go into the near future, we see the emergence of persistent memory in that second pyramid, I should say. And now that is a gap filler, if you like, between the world of block storage. Again, disk and SSD are still very prevalent. DRAM, of course, very prevalent. But now we have this notion of persistent memory, which can be in two different forms, block addressable, but also byte addressable. And I'll go over that here in a bit as well. And then moving forward in time, what we're going to see, and in fact, many vendors in the industry are already working on, is what we call on-package memory, or OPM for short, which means that memory resources and processing resources would literally be in the same physical package. So you might see this in the form of ASICs or FPGAs or other non-types of CPU processors, but you would also begin to see it in CPUs. Now, we already know that CPUs have had a form of on-package memory for quite some time. We call it cache, typically made of static RAM or SRAM, but you will see more emergence of new types of memory technologies. And you can see some of the alphabet soup there on the right, things like high bandwidth memory and resistive RAM and magnetic RAM. And by the way, the SNIA has an entire presentation on forms of memory like that. We will not go into detail about the forms of persistent memory, that different media types, but we wanted to give you an idea of how the memory and storage world is evolving and indeed converging. Memory is now storage, storage is now memory. All right, the vision for persistent memory as well. Again, the SNIA is composed of hundreds of different companies and individuals, and we do have a vision for persistent memory. It's pretty straightforward. We want to educate the general public and the consuming public of technology that persistent memory is fast like memory and persistent like storage. It's basically as simple as that. The emergence of these new technologies which allow those two characteristics to take place. And then in terms of implementation, you can think of persistent memory literally as bringing storage to memory slots. We all know what servers and laptops and desktop machines look like. They all have slots for memory. We've been familiar with this type of design for decades. Now imagine the world of literally persistent storage in the form of memory being placed in those memory slots and the systems being able to use them, in particular for acceleration of general workloads, but also some very specific workloads like real-time data capture and analysis to provide a much more real-time response and amplify, if you like, the ability for systems to provide machine learning and AI and other topics which are now beginning to be front and center in the industry. So we really like the vision for persistent memory here. As Alex mentioned, we think it's one of the breakthroughs that the industry has been able to provide in quite some time now. Okay, let's break persistent memory down and put a taxonomy around it, if you like. We've been discussing persistent memory, but in particular, it is a type of a larger set called non-volatile memory. And really, persistent memory is the bottom bullet there. It is memory-like NVM. This is what we call persistent memory. And the memory-like characteristic is very important because of the way that this media is presented to operating systems, hypervisors, and applications. They are presented as byte-addressable memory regions. In other words, I'm not really doing I.O. in the classic POSIX sense of the word. I'm doing load store operations where my data to be persisted is in a CPU, it's being processed, and the straightforward way to persist this data is to store it in memory using byte-addressable techniques. Now, this is as opposed to, or more importantly, in conjunction with, the disk-like non-volatile memory, which we really don't call persistent memory. Again, we're distinguishing memory and storage on its accessibility because disk-like NVM really appears as a disk drive to the application. You can think of it as a virtual disk if you like, but it's accessed as a traditional array of blocks. I have an address, I have a link, I want to retrieve or store a number of blocks. Off you go. We've been doing this for decades. So those are really the two forms that we'll be talking about in the deeper dive to come. Now, finally, the characteristics, again, to reiterate about persistent memory. The most important one is definitely byte addressability. So if you're programming, and Stephen will elaborate on the NVM programming model, this is a key characteristic, and it provides certain benefits as opposed to the disk-like non-volatile memory in that it's not prone to unexpected latency. Some people call this tail latency or 99th percentile latency, if you like. But these are the characteristics of persistent memory. Again, memory-like performance, fast-like memory, persistent-like storage.
Thank you, Rob. So, before we move on to Stephen, I just want to put in a little announcement in the area that you can see where I'm showing an announcement. It's actually, we've got quite a lot of acronyms we're going to be covering today, and I know it can get a bit like acronym soup and can get a little bit confusing. SNIA helpfully have a dictionary. So there's a link there in the announcement part you can see where you'll get all these acronyms explained. If you just click on that link, it's organized in the usual way, A through Z. So thanks very much, Rob, for that explanation. We're now going to hand over to Stephen. Just a reminder, by the way, if you need to ask a question, please do so. But Stephen's going to talk us about the NVM programming model. Take it away, Stephen.
Thank you very much, Alex, and thank you, Rob, for that excellent introduction and overview of persistent memory. So my name is Stephen Bates. I am a member of what's called the SNIA Persistent Memory Technical Working Group. And together we've developed something called the NVM Programming Model, which is really about how we have a vision for connecting applications to persistent memory. And I'd like to spend the next few minutes digging a little deeper into what that NVM programming model is and the impact that that programming model is having on real-world use cases and real-world software stacks for persistent memory. So the SNIA provides a leadership role, and this is something that Alex mentioned in one of the previous introductory slides. SNIA's charter includes advocacy and thought leadership around new topics in storage and persistent memory. And so quite a few years ago, we realized that there was a need to address this emerging technology of persistent memory. As Rob pointed out, this byte addressable, low latency, persistent types of technology that were coming to the market. And so what we did is we formed a technical working group, what we call a twig, to take a task to go and look at how are people going to use this new type of technology, and more importantly, how are we going to make it do really interesting things at the application layer. Because the reality is having a interesting new material technology is somewhat irrelevant if we can't derive some benefit from it at the application layer. So we took a very application-centric view of persistent memory, and I'll talk about that in a minute. SNIA is obviously not aligned to any one particular vendor, so we took a very vendor-neutral approach. And one of the things that we wanted to do is to make sure that the work that the NVM programming model came up with was applicable today. We could use it with persistent memory technology that you can go and buy on the market today, and that didn't require some kind of future technology that may or may not come to fruition. So very important that, you know, some of the things, or all of the things that I'm going to talk about here, can be done today with persistent memory technologies, including some of the technologies that Arthur's going to talk about in the final section of today's tutorial. And we also wanted to take a look beyond storage. You know, SNIA typically has a very storage-centric focus, but we realized, and Rob also alluded to this, that persistent memory does more than just store data. It gets data, persistent data, closer to the processors, and that means that we can do things quicker with it, we can search it quicker, we can analyze it faster, we can use it in our applications in new and interesting ways. So we wanted to take a more than storage approach to persistent memory. So we focused on applications, we focused on memory semantics, so using loads and stores rather than the more traditional I/O stacks. We're looking at networking and persistent memory and things like persistent memory over fabrics, which is a very interesting topic that I'll touch on briefly, but it is a very lively topic within SNIA and the industry in general right now. And also the impact that persistent memory has on processors and processor architectures, and potentially even pointing in the direction of new processor design. So it was a very large mandate that the group had. The mission really was twofold. The first part of the mission was to accelerate the availability of software that enables persistent memory hardware. So like I said, having a persistent memory piece of hardware is not particularly interesting if you can't do fun things with it at the application layer. And so part of the programming model TWIG's mission was to help software developers come up with a framework that they could follow in order to connect applications to persistent memory in a way that yielded the value of that persistent memory. The hardware does actually include both solid-state drives and persistent memory. So Alex earlier mentioned, you know, should it be persistent memory programming model? Well, because we do touch on how you interact with a solid-state drive, which is a block device, it's probably more correct to stick with NVM as opposed to PM programming model. But obviously the hardware and a lot of the focus of the TWIG was not so much on the SSD side, which, like I said, is a block device, but on the persistent memory, which is a byte addressable device. And that's a very key difference and one that Rob mentioned earlier. When we looked at the programming model, we did try to separate between things that we felt should be in user space and available to user space versus things that could potentially be in the operating systems, or, you know, what we refer to as kernel space. So there's a division there and a demarcation between those two different parts of the software stack. And then we actually wanted to create the NVM programming model, and you know, I'll talk a little about this in a minute. But basically, there's a downloadable document which defines the programming model, and it defines it in terms of visible behaviors. So what are the kind of properties that we expect persistent memory and solid-state drives to have? What kind of attributes do the applications need to be aware of in order to maximize the benefit of those particular pieces of hardware? And how do we actually talk to those devices? The NVM programming model is not itself an API. It's not a programming interface. It is more a framework for the development of APIs. So we don't fixate on any one particular implementation. Rather, we provide a more general roadmap or guideline to the industry so that people who are developing APIs have a model that they can follow. And it definitely exposes some interesting ideas around where things might go in terms of both networks or fabrics, if you want to call them fabrics, and processors. And I'll touch on those in a minute. So where are we in terms of the NVM programming model? Well, right now, version 1.2 is the most recent version that's been approved by the SNIA board, and that was approved in June 2017. you can download that at the URL that's provided here on this slide, and you can also download the previous versions and actually look at what was actually done as we went from 1.0 to 1.1 to 1.2. And this is a living document, and the programming, the twig is a programming, it's a live entity. So if anyone's interested in getting involved, please reach out. We are definitely looking for contributions, and we are looking at a couple of very interesting new areas that I'll talk about in a moment. We expose new block and file features to applications. As Rob said, one of the key differences between classical storage and persistent memory is byte addressability. Another one is the low latency and the guaranteed low latency, the quality of service, for want of a better word. And we expose those kind of features to the applications so they can be aware of what they're talking to, and then they can basically tune themselves to maximize their performance, assuming you have this kind of hardware in your system. But there are things we have to be very careful about. Atomicity is one of them. With a block device, for example, when you write a sector, which could be as large as 512 bytes, you're guaranteed that 512 byte change to the data is either going to happen in its entirety or not at all. Byte addressability is really exciting from an application acceleration point of view, but it poses interesting challenges about what happens if you want to write a larger amount of data, but there's a failure event or some kind of power loss event that occurs halfway through. Memory mapping of persistent memory raises some interesting challenges. We've been memory mapping files for a very, very long time, longer than I've been in the industry for sure. But now these memory map files are potentially persistent right at the byte layer, and that raises some interesting challenges about how the mmap interface in Linux or the map interface in other operation systems should be modified in order to take advantage of this persistent memory and be aware of it. And then the final point here is really one I've already said. The programming model is not an API. We don't describe it in terms of software or code. It's described in terms of formal definitions. I do suggest everybody download the document if you're interested and take a look. It's quite an easy to read document. It is there to help software developers and API developers to come up with APIs that are going to work very nicely with persistent memory. So, one of the key points of the NVM programming model is that it has 4 modes of operation, as we call them. And 2 of those modes are related to block I/O, and I'll talk about that in a minute. And Rob touched on this earlier. And 2 of those modes are based on persistent memory, emerging NVM technologies, which we should really call persistent memory. And I've highlighted those 4 different modes in red, using the same nomenclature that we use in the programming model. So we have NVM.file and NVM.block, which are the way in which we would access a block device, which could be either a solid-state drive, which is inherently a block device, or it could be a persistent memory device which has a block driver on top of it. And I'll show a little bit more what I mean by that on the next slide. So we can take an NVDIMM, and rather than having to adapt our applications to become persistent memory aware, we can, in kernel space, put a driver between the application and the NVDIMM so that it looks like a block device to the application. Now, it still might be incredibly fast for a block device, and so there may be some benefits to doing this, though you won't get all the benefits that persistent memory has to offer. But maybe it's enough for what your application needs, and maybe the next step of persistent memory is a little bit too much for you to take on right now. However, if you're more aggressive and you're more adopting of the persistent memory type of approach in your applications, you're probably more interested in the access methodologies that are in the right-hand column of this table, which are the NVM.PM file and NVM.PM volume, which actually present memory spaces directly to the application. The application is no longer talking to a block device. It's not a block API anymore. It's a byte addressable memory style API. Load stores can be used directly against these devices, either as a flat memory space or even as a persistent memory aware file system, which is the PM.file. And you get the benefit of the low latency and the byte addressability and the persistence. And this is definitely probably the most kind of topical and interesting of the access methodologies. So like I said, the NVM.access methodologies, NVM.file and NVM.block, are probably ones that people are more familiar with, in the world of POSIX operating systems, standard block APIs. Data is normally buffered by using a RAM buffer in system memory. So you may use something like a page cache, you may just use a bounce buffer, and then basically software controls how that I/O is then passed to the block device, often using some kind of DMA that's available on the block device itself. And then the software also controls whether you do this asynchronously, i.e. can you context switch to something else while the I/O happens. Certainly in the days of spinning disk, it made a lot of sense to do that because I/O took a long time. With solid-state drives, these low-latency NVMe drives, it may not make sense to context switch. And in the case of a persistent memory block device, it really may not make sense to context switch because the access times could be on the order of a couple of microseconds, which is equivalent to the overhead of a context switch. But that really depends on your processor architecture and so forth. If you're not context switching, you probably want to poll for completion so you know when the I/O is done. And the programming model provides, agnostic methods by which that can be done. And the status is explicitly checked by software. The NVM.PM modes enables load stores directly. So rather than doing load stores to a bounce buffer and then doing an I/O DMA, when we do load stores on the NVM.PM models, regardless of whether it's a file or a volume, we are directly changing the persistent media itself. And that's a very interesting, exciting, and perhaps a little bit scary change to the I/O model, because now we have things like atomicity to worry about. We have to worry about corner cases about what fails. And in the case of the file system, we have to worry about atomicity even more in the sense that if there's a failure between the data change and the metadata for the file system change, very bad things can happen to your file system, which is never a good thing. So there's a lot of opportunity, there's a lot of potential for benefit here in terms of application acceleration, new workloads, new ways of doing things, but there are challenges, and part of the programming models group work was to address those challenges. So, I talked a little about the block mode access. If we look at that from a diagram point of view, you can see exactly what I talked about earlier. If we look at the diagram on the right-hand side here, you can see at the very bottom in the dark blue, we have a persistent memory device. And that device basically talks to a block device driver that's sitting in kernel space. And then we have some persistent memory block mode extensions that basically allow block-aware applications to communicate with the persistent memory device. Notice that those block-aware applications could be legacy applications. A block device is something that's been around for a long time. Spinning disks are, block devices. So we're very comfortable working with them. It's just that some of the attributes of a persistent memory block device are different than they are from some of the legacy devices. So we may have things like alignment issues, the atomicity length, for example. If there's a certain length of operation that's optimal from an atomic point of view, the block device may decide to advertise that, and the block-aware application, in order to be maximally performant, may need to be aware of that. So there may be things that we need to do there. The file operations then obviously also have some attributes that they would like to make aware to the application. So we may have things like, again, atomicity attributes that we want to make aware to the user space. And we have essentially a programming model to allow that to happen. So that's maybe a little more traditional. Now, if we move to the persistent memory modes, it looks somewhat similar, but we do have a change in the sense that we're no longer in a block device paradigm. So now we have a persistent memory device that is essentially a flat memory space that can be accessed by load stores. If we look at the diagram on the right-hand side and look at the very right-hand side of that, you can see the dash line, and that's the lowest level of access that's possible from user space to kernel mode, which is basically load stores on the processor, directly manipulating memory spaces on the persistent memory device. So for example, in an NVDIMM, this is really just you talking directly to the NVDIMM memory from user space. So almost equivalent to the ODirect POSIX command, but for persistent memory. And that's really the lowest level way that you would access the persistent memory. But we do have other ways of extracting the device. One of them is the PM volume mode. PM volume is interesting because it can take multiple persistent memory devices and present them to the user space as a single device. Why would that be interesting? Well, RAID for one. So if you wanted to have multiple persistent memory devices and still have some kind of data resiliency in the case of a media failure, the PM volume mode allows you to address that. You may want to have striping in the same way that we use RAID 0 today for block devices, and that is something that the PM volume mode allows you to do. On top of the volume mode, we obviously have persistent memory aware file systems, and this is a very interesting and topical space. There's a lot of really good research being done around persistent memory aware file systems, and I'll talk a little about that in the next couple of slides. Persistent memory file systems have to be cognizant of the fact that the data or the media they're talking to is byte addressable. It has different failure mechanisms than a block device, but you still want to present all the advantages of that persistent memory device to the application. So it's a very interesting space, and we've done quite a bit of work there in the programming model addressing how that link between the persistent memory device, the persistent memory aware file system, and the persistent memory aware applications can all interact in order to get very good performance at the application layer. So maybe just talking about a couple of the more interesting things that we can do with the persistent memory programming model. I mean, one of the things that we talk about in quite a lot of detail in the programming model documentation is the mapping of persistent memory. So like I said earlier, mmap in Linux, for example, or mmap as a POSIX command has been around for a long time. We're very familiar with doing memory maps on either files or regions of memory or so forth. But doing that with persistent memory, it raises some interesting challenges around corner cases of failure events. What happens when power is lost? Can torn sectors occur when you have some kind of pseudo block device on top of the persistent memory? And that's something that we spent quite a little time working with and defining sets of attributes so that applications can try and manage those error events reliably. Synchronization is a really big problem, and this is something, if anyone's been to any of the recent storage developer conferences, SNIA, organized in September, will be aware of. How data is written to these persistent memory devices is very CPU architecture dependent. Caches are in the way. Those caches are there for a reason, a performance reason. But for persistence, they can be a challenge on the right path because data can get stuck in the cache. And how do you know it's got to persistent memory? So that's something that we spent a lot of time working on. And we've even seen some changes to processor architecture occur recently around optimized caching, optimized cache flushing. So not flushing entire caches, but flushing ranges of either pages or cache lines. And then there's challenges around ordering. So if a CPU cache is written to by load store commands, but we then flush the cache in a different order to the writes, then there can be some challenges, especially in file system mode. And that's something that we're actually actively working on in the programming model today to try and define that in a safe and reliable way. Another problem that we're looking at is the atomicity of failure domains. Processors today are very complicated, multi-core systems with multiple sockets potentially, with coherency buses and coherency protocols that cross multiple sockets. So because we're now talking persistent memory, we have the ability for a core that's potentially on a different socket to the persistent memory device trying to interact with that persistent memory device. Failure events can occur where single sockets die, where multiple sockets die, where the memory dies, where the media on the persistent memory dies, and all of these can lead to different challenges, different corner cases for these different persistent memory access modes. And again, the NVM Programming Model Technical Working Group have worked on pretty extensively some additions that went into 1.2 around some of these issues, around handling failures in multi-processor, multi-core systems, and how does the surviving cores potentially recover from these events. So how do we handle a system failure? How do we handle partial system failure? How do we handle a complete power failure? And how do we handle memory, either memory failures of the entire device or even media failures where part of the device fails? And there's a whole kind of paradigm of approaches to doing this that are there in the NVM programming model. And you know, there's a range of ways in which we can address those issues, and those have been discussed there. So, you know, there's an awful lot of work that has been done by the NVM processing twig. It's really good work. I do suggest people go and review what we've done already. There's also a lot of work that's actively being undergoing right now. So I mentioned all the error event type of work that's went into 1.2. We are looking at issues around high availability. So can we have multiple copies of data in multiple persistent memory devices? And can we have multi-path between the processors and those devices so that if something fails, we still have an alternate route to the data? And that's something that we've done a white paper on. We're looking at things like asynchronous flush. So is there the ability to move away from this load-store model where loads and stores are blocking operations, or flushes are blocking operations, where we can actually do flushes as asynchronous tasks and perhaps come back and check when they're done? And that's something that I think the CPU vendors are also looking at, and we may see a case where something's proposed in the programming model and we actually see CPU vendors evolve to take some of these characteristics into the hardware that they provide in their future offerings. We're looking at persistent memory security for multi-tenancy. This is a really big issue. A lot of cloud vendors are running many virtual machines on a single bare metal server. Those bare metal servers may soon be equipped with large amounts of persistent memory. How do they secure and isolate the tenants that are sitting on top of those hypervisors? A very interesting area, and that's something that was discussed at Storage Developer Conference and continues to be part of the programming models work. So, you know, just to summarize and provide some real-world examples, the NVM programming model has acted as a guide, and it is helping to align the industry. One of the really nice real-world examples of persistent memory APIs is pmem.io. I suggest anyone who wants to learn more about, you know, playing with persistent memory and even trying out some code, go visit that site and the associated GitHub sites. There's a lot of really good library work done there by you know, a range of different companies. It's helping to define common terminology across these different OSs and APIs. We're not forcing a specific API, but we're helping everyone converge on the same kind of language. And you know, the work that we're doing today is summarized on the link that's provided, you know, in that third bullet in the top section of this slide. You know, what are some of the things that we're doing with it? Well, we're helping to define persistent memory models in real operating systems. So, you know, one example of that is direct access, or DACS, as we call it, aware file systems in Linux. And anyone who's interested in that, I, you know, grep through the Linux kernel code for FSDACS, and you'll find some good information on how to use that in Linux today. There's some really good user space examples that exist. Again, if you go to the NVML, so the non-volatile memory library GitHub site, which is part of the pmem.io work, they have a really good examples folder. You can go and play with that. And then we obviously have some new technical working group work items that we're working on. And I think one of the final things that I'll say today is that we're at a very exciting juncture for persistent memory. We have NVDIMMs that Arthur will talk about already. We're looking at emerging memory technologies. 3D crosspoint has been seen a lot in the press recently. You know, Intel have publicly said some of the things they're doing in that space, and I have no doubt that others are also doing work in that space. So this is a really good time to get involved in persistent memory. And if you want to get involved in the technical working group, please reach out. We'd love to have you and bring you in on board. So thanks very much for that, and I'll pass on to the next.
Thank you, Stephen. I've actually got a question for you, Stephen, that's come in from the audience. Does SNIA or anyone else publish a list of vendors or products which are already NPM version 1.2 compliant? I think I know the answer to this, but do we have a list of people who are complying with this standard or not?
That's a great question. I don't know the answer, Alex, so I'm going to let you have a go at it.
I think the answer is there aren't any. Yes. But Rob, Arthur, do any of you know whether anybody's claiming victory?
Well, yeah, Alex, very good. Let's put it this way. So in general, the SNIA is not an organization which would certify a product. Now, having said that, we've developed models that others have used in order to certify or test certain products. For example, the Solid-State Storage Initiative did very good work in creating a test suite that many vendors and consumers of SSDs have used. So the SNIA's role is to not, to use a term, bless a product or not. The SNIA's role is to construct frameworks like this from which others, both in the vendor community and the user community, can test certain pieces of equipment or certain devices to their heart's content. So that's the role of the SNIA in this role.
Okay, thank you. That's an excellent answer. So I'm going to put up again another display announcement, which is the link where we're going to put the copy of the slides, because I know there are a number of links in the slides and you may want to see them. So that's the link where we're going to put a copy of the slides. It's a blog address. And we'll also do a brief Q&A, and that'll be posted in the next few days so that you can actually see the presentation in all its glory, get the links, and also get any Q&A that we didn't manage to cover during this session. So thank you very much, Stephen. That was excellent. That was actually very detailed. A lot of really good information in there. Now I'm going to invite Arthur, who's going to talk about the actual physical packaging of this persistent memory. Over to you, Arthur.
Thank you, Alex, and apologize for any background noise you might hear. All right, so let's move forward here. First of all, the NVDIMM Special Interest Group was formed approximately 4 years ago, and the purpose of the group within SNIA was to help collaborate and focus the development activities, the ecosystem activities for support of NVDIMMs in the industry. We are still welcoming members, so if you'd like to participate with us, we would welcome you as well. But really the mission has been to communicate what is an NVDIMM, to communicate some of the development activities, and also to work with JEDEC in helping to standardize some of the specifications. Okay, so what are the NVDIMM types? First of all, there's the NVDIMM-N. This was standardized by JEDEC in October of last year. The specification was published. The NVDIMM-N type is essentially a registered DDR4 DIMM. So when you plug this DIMM into a NVDIMM-enabled server, it's going to come up as a registered DIMM with access to the DRAM. There is no access to the non-volatile memory that would be on that NVDIMM. The data on the DRAM, if in the event of a power loss, would be transferred to the flash. So if the system loses power, the data transfers from the DRAM to the flash, and there's a power source required for that NVDIMM to hold up the DRAM long enough for that data to transfer from the DRAM to the flash. It is byte addressable, just like DRAM. It has high-speed access, just like DRAM, and it has the endurance of DRAM. And the communication occurs over the SM bus. There's two standards there. There's a JEDEC standard, and that's mostly being followed today. And older systems, we would have what's called a legacy command set, which is also supported. It's typically a firmware change to support either the JEDEC command set or the NVDIMM or the legacy command set. What's being worked on now at JEDEC is the NVDIMM-P. Essentially, there's a media controller on there. What's behind the media controller is agnostic. It can be any type of non-volatile memory. It can be a combination of high-density DRAM as well. and that would depend on the manufacturer of that NVDIMM-P. What's being standardized is the protocol on how that NVDIMM-P is seen on the memory bus. It's a transactional access, which is decoupled from the media and can support multiple media types, as I mentioned. And also the latency, you can see there from nanoseconds to microseconds, depending on what type of media is used behind that media controller. And the plan is to support a DDR4 NVDIMM-P as well as a DDR5 NVDIMM-P, and the plans from JEDEC are to standardize that in 2018. So what we're showing here is a cookbook of sorts. It has all the pieces of an NVDIMM-N, from the very top, the application and the file system, which Stephen talked about. There's 3 different modes there. There's the block and the page caching block file storage, the persistent memory-based file system, and the DAX enabled. So there's various ways that the NVDIMM can be utilized in the system. The BIOS needs to be specifically enabled to support NVDIMMs, so when that NVDIMM is plugged in, it is recognized by the host and can be configured properly. Same thing with the memory reference code on the server, that also has to be NVDIMM enabled, which there are approximately 30 or more systems available today, industry standard systems that do have NVDIMM support as a standard option. And then on the very bottom, you have the NVDIMM-N combined with an energy module that's used to provide that backup power to the DRAM long enough for the data to be transferred from the DRAM to the flash. So that's a quick model of the ecosystem surrounding NVDIMM-N. So in terms of applications specifically on NVDIMM-N, primarily they align with the densities of registered DIMMs today, so 8, 16, 32 gigabytes are the primary densities for NVDIMM-N. They're primarily used for logging functions, so journaling, log acceleration, tiering, caching, write buffering. Those are aligning with the densities associated with registered DIMMs versus entire memory databases, which would be stored in persistent form of memory. So primarily the NVDIMM-Ns are used as storage servers for log acceleration. Lastly, on the bottom there, they're also used for checkpoint acceleration in high-performance computing applications. So here's a quick snapshot of that, the transaction logging. So instead of going through the block device layer and to the flash, you have 2 elements that are slowing things down. You have the I/O overhead, and you have the flash media itself, which are inherently slower. When you're using NVDIMMs to do your logging function, you're going directly into DRAM memory, which is made persistent with the use of the flash on the NVDIMM-N. So with that high-speed access to persistent memory, DRAM, you're able to provide system acceleration for those file transactions and the logging system functions. Just some updates here on the operating system. So today the Linux kernel 4.4 and above has native support for NVDIMM-N. Previously, specific drivers were required in the operating system to be able to recognize NVDIMMs. So the input table has been added. There have been many, many changes to provide this native OS support within Linux kernel 4.4 and above, and that has enabled quite a few systems to be shipping today using Linux and supporting NVDIMMs. So that was one of the ecosystem developments that the NVDIMM SIG helped to promote. Also, Windows, the Windows Server 2016 operating system does also have native support for NVDIMM-N, and you can see the different modes of access here: block mode, direct access, which Stephen mentioned as well. So here's an example. This is a Windows server, a server loaded with Windows operating system on it. It's a logging function, a SQL database, and it's a bit hard to see in this particular chart, but what you're seeing here is 4 different levels. On the far left, the dotted blue line, the dotted red line are NVDIMM-enabled systems combined with either a rotating drive or a hard drive, and the scale of access on the bottom is logarithmic. So you're seeing tiers of speed increase going to the left for much faster latency associated with accessing the logging data in DRAM. So that's there's a couple links that I can add to the slide which show this demonstration live, which was given by Microsoft. Okay, so in summary, the NVM programming model has been combined with NVDIMMs to really create the vehicle for promoting persistent memory. Stephen or Rob, if you'd like to make some summary comments as well.
So it's actually Alex here. I just want to make one very brief comment, because I think this is one of the things that struck me about the whole thing that I didn't realize. When you look at this as a new technology, the one thing I think that's really quite striking about it is that we're talking about latencies and bandwidth that are so many factors greater than what we've been used to with disk. And the real change here is that we are now looking at stuff, instead of talking about your milliseconds access time on spinning rust, we're talking about microseconds. We're getting down into the high hundreds of nanoseconds in terms of latency. I mean, this is technology that is really going to turn the way we think about storage, and persistent memory is a real game changer. It's not just another, faster, slicker, quicker, etc. It's much more than that. It's a real game changer. I don't know whether either Rob or Steve wants to come in on the back end of that.
Yeah, Alex, it's Rob. Just one comment on that. I totally agree with what you and Arthur have said, but going even further, consider the way that we, the computing industry, have structured our systems around the concept of a relatively small, very fast, relatively expensive area of volatile memory directly addressed by the CPU, so byte addressable, and then a relatively large, relatively slow area of persistent block storage. Obviously, this type, this twofold type of architecture has been in place for literally decades, since the introduction of static RAM several decades ago. Now, today, with persistent memory, we have the chance to, and I'll use this term, breach the gap in terms of volatility and non-volatility, but also, to your point, Alex, in terms of latencies. Now we have persistent media, which is, again, very low latency, memory-centric, byte addressable. So imagine the way that operating systems could use this instead of caching, disk blocks in memory buffers. Imagine the way that file systems can use this, and in fact, with some examples here, the use of file system metadata, which we in the file system world know is absolutely key to good performance. And then beyond that, the fact that applications and databases in particular for decades have used memory as a caching area, literally just to hold disk blocks and overcome the large, several factors, as you mentioned, Alex, differences, orders of magnitude in the ability for that persistent device to actually transfer data into memory. And if your data is in memory, you're not computing. That's the fundamental approach to the way we compute. So having your data persistent in memory, available to compute at high nanosecond or low microsecond latencies really is a breakthrough, I believe, in the computing industry.
Couldn't agree more.
Yeah,
really exciting times.
Just to add to that, there was this guy at Storage Developers Conference called Stephen Bates who did a keynote on low latency block devices. And I think, there is technology that allows low latency block devices to get down there in terms of latency, but I think what Rob said is absolutely correct. It's more than just the latency. I think the really interesting thing about persistent memory is the latency combined with the byte addressability and the fact that the processors can load store directly to the data. Because we can do low latency block devices, and they're good, and we're going to use them in systems, but I think for persistent memory, there's a real advantage over even those low latency block devices because of the byte addressability. And I think that's the most exciting thing. And Rob, I definitely share your excitement in terms of how we are going to use that. It's going to really change a lot of things in compute architecture and applications over the next 5 years.
Excellent. Thank you very much. I'd like to thank the three of you, and I'll do so properly at the end. But I want to just point out that we're running a Persistent Memory Summit, the 6th Persistent Memory Summit, in San Jose in California, at the Westin, which is formerly, some of you may know, as the Sinclair Hotel, on the 24th of January. Free registration, complimentary to attend. We might even find a sandwich or two to provide you with during the lunch break. But the space is limited, and I put an actual link into the audience announcement piece so you can see, where you can actually see details about the Persistent Memory Summit. And we're going to be covering in a lot more detail some of the things that we've covered today, and the technology. We're going to talk more about the programming model, and we're going to talk about real use cases and where we're going with this stuff. It really is quite an exciting time. So there are lots of resources. There are SNIA white papers, there are summits and webcasts on demand, there are technology videos on YouTube. What I will do, though, is make sure that we take any of the questions we've had from the audience that are unanswered, and I'll make sure that all this information is available on that SNIA SSSI blog, and that we get copies of this and pointers to all the relevant parts of the SNIA website. If you want to investigate the SNIA website directly, it's fairly simple. It's SNIA.org, and you'll find us under either SSSI or PM for persistent memory. So I'd like to thank Rob Pegler, I'd like to thank Stephen Bates, and I'd like to thank Arthur Senio for providing us with a very interesting presentation on the state of persistent memory technology. As you leave today, ladies and gentlemen, I'd be delighted if you gave us feedback. Remember, the feedback score is really simple. 1, we should stay in the golf course. 5, that was excellent. I want to know more. In the meanwhile, Rob, Stephen, Arthur, thanks very much today for your presentation. The audience, thank you very much as well for attending, and have a good rest of your day. Thank you very much indeed. Bye now.